So for that first reaction, what happens? It's just a standard reduction. We'll turn that ketone into an alcohol. You notice there's one slight variant. We added HCl instead of H2O. Okay. Why? Don't mess with your head. That's about it. Okay? That's not going to do anything. If it was excess HCl, that might be a problem. Why would it be a problem if we did excess HCl? We protonate the alcohol, which then turns the alcohol into what? A good leaving group. Would there be any, say, other nucleophiles floating around, like chloride? That's a Cl. So if we went under excess conditions, then we could potentially see a substitution reaction occurring. Okay. We don't have excess, it's just dilute HCl. Okay. So we should stop just at that alcohol. Next one. Just a standard reduction. We're again converting that across, nice and simple, over to our benzyl alcohol. Okay, nothing fancy. Next one. Actually asking for something slightly different here. We're going backwards. Sodium borohydride reacts with what? Carbonyls, which means we need to have a carbonyl in our starting material, so we can convert our alcohol back to the aldehyde. Okay. Last one, very similar pattern, and I know it's a lot of people jumping out and giving me something along these lines, and then saying your borohydride. Not a bad idea, except what other information were you given? You had a broad peak in the 3,300 to 2,800 range. That 3,300 to 2,800 is what? An OH due to carboxylic acid. Okay? So your starting material is actually the carboxylic acid, which causes a wrinkle. Does this reaction work as shown? No, we can't use sodium borohydride. We'd have to use the lithium aluminum hydride, do our two-step fun stuff, lithium aluminum hydride and water. Okay. Just as a random side note, I happen to be thinking about the sapling thing. If anybody remembers when we talked about these reagents, they always did it as a three-step, and they said ethyl acetate. Anybody remember that? Vaguely from the sapling homework, they broke it down into three steps. I've decided that I think what that ethyl acetate is there for is to neutralize the LAH. So ethyl acetate is an ester. It will react with the LAH, excess LAH, to quench the LAH reagent, and it will produce methanol and ethanol, which is easily pulled out of the solution. So I think that's why they're having it there. Still not sure exactly, but that's my best guess, is the ethyl acetate is being added as a lab step to neutralize the LAH, just so you know. Okay? Still, as far as class goes, really all I would expect is you to give me it as two steps, LAH followed by water. Okay? Nice and straightforward, a little bit of practice just to warm you up. When we move up to, I don't know why I'm calling them super carbonyls, but I am. These other functional groups are acyl chlorides, our esters, and our carboxylic acids. Okay? Lithium aluminum hydride did a great job of reducing these. Okay? And that's because in most of those circumstances we have some kind of leaving group, it's best seen with the chloride, that our lithium aluminum hydride supplying the hydride can attack, break open to our tetrahedral intermediate, which can then reform our pi bond and kick out the chloride as a good leaving group. We would then shift to having an aldehyde. Well, the aldehyde is still fairly highly reactive, and so our lithium aluminum hydride could attack again, and we would end up pushing all the way down to the primary alcohol. So those three functional groups are kind of interesting in the respect that we could potentially reduce all the way down, depending on how far we wanted to go. With lithium aluminum hydride, we couldn't really stall it, though. Okay, so lithium aluminum hydride is forced to go all the way to the primary alcohol. And that's because the hydride is too strong of a nucleophile in this case. Sodium borohydride, a weaker hydrogen nucleophile, is now so weak that it can't interact properly with these functional groups, and it won't react with them, period. Okay? So kind of interesting effects happen with that. But DIBAL is now our new reagent, and DIBAL does react with carbonyls, and it reacts selectively as single reduction steps. So it's a pretty big difference from our lithium aluminum hydride. So if we reacted DIBAL with an acyl chloride or an ester or a carboxylic acid, we can stall that reaction at the aldehyde, which is kind of interesting. Okay, so the question becomes is why? So what's the key difference between DIBAL and, say, lithium aluminum hydride? Anybody notice any differences? What's that? There's only one hydrogen attached to it. So that's a big key difference. So that when we go through to measure out the lithium aluminum hydride, we aren't losing track of how many hydrogens are actually being added into the solution. There's only one hydrogen being supplied by DIBAL. So that's kind of a big difference. What else is a big difference? We're going to have a steric effect. Okay, we've got those large isobutyl groups. Draw out the Lewis structure for our aluminum hydride. Is this the correct Lewis structure? No? Why not? What's wrong with it? Yeah, it needs to be charged. We have a negative charge. If we look at DIBAL hydride, do we have that negative charge? No. That's one of our other big primary differences with this species, is that DIBAL hydride does not generate a ridiculous hydride active nucleophile. It's still present, but it's controlling the presence and the reactivity of the hydride that ends up changing the dynamics of what DIBAL does when it goes through and reacts. Okay? So we'd have to look at a slightly different mechanism for this. So if we take a look at our DIBAL hydride, actually it's before we even do that, let's take a look at lithium aluminum hydride. On the bottom, if we were going to go through and do that reaction, our first step was what? Resonance is not a step. So resonance allows us to see that our carbon is positive and our oxygen is negative, but that is not a distinct step. The hydride attacks our carbonyl carbon and moves up, and that's because we have that negatively charged hydrogen. So that's our primary first step. When we move to DIBAL, our mechanism changes. Any guesses? How does it change? Nope. Hydrogen's got to stay attached. It's too unstable for it to float off on its own. The oxygen is going to attack the aluminum. Okay, why might it do that? The oxygen is negative and the aluminum isn't officially positive, but what's the hybridization of the aluminum? sp2, which means what's left over? An empty p orbital. What can we put in that empty p orbital? The electrons from our oxygen. Once those electrons have shared, we then end up in a new situation. I'm not not sure how I can draw this neatly, but we'll attempt it. We're now our groups are out here. We've got our oxygen connected. Does oxygen want to be positive? Whoops. A double bond to our carbon, and then it's junk. Our oxygen would be formally positive. Does it want to be positive? No, so what does it do? Takes electrons from the pi bond, which then means the carbon is positive. What happens? Now the hydride attacks. Right. This facilitates multiple bond cleavage, where we end up with, as our product, an aluminum oxide. Whoops, come back here, oxygen. Pretty much the same result that we've seen before. Should probably draw that structure right. There we go. Same overall result. We've added the hydrogen to our electrophilic carbon. Okay, but we did it in one step. We did it, or not one step, but we did it in a slightly different order. And that order had to do with the reactivity of our hydride nucleophile, or how it's getting into that. Okay. Now what happens at the end of this? Well, we still have to cleave our oxygen-aluminum bond, so we add our water or our acid. Okay. The dilute water can come in, kick out, and we can pick up our H+, and we'd have our alcohol. Okay. What happens if we switch to an acyl chloride? Well, the oxygen electrons can shuttle back down and kick out the chloride. Okay. So what we'd end up with was an intermediate, potentially a reactive intermediate. So let's draw those out now. Okay, so if we went through and said that we had a chloride in there, what we're saying we'd do is we'd end up at this position, okay, with our chloride floating around. That becomes problematic because that was the same issue that we had with our lithium aluminum hydride. We formed that aldehyde, and now the aldehyde, being more reactive, reacts with a second equivalent of our lithium aluminum hydride. But in the case of DIBAL, it doesn't react. Why? What's the reactive species? The electrophilic carbon or our oxygen? If it's the carbon, look at that very first step of our mechanism. What attacked? The carbon do anything? The very first curved arrow shows the carbon did absolutely nothing. Okay? The difference is that our oxygen is now acting as a nucleophile with DIBAL. And we move to the aldehyde, we've changed the activity of that oxygen because if we look at either our esters or our acyl chlorides, all of those extra functional groups have lone pairs. Those lone pairs, through resonance, can potentially donate in, making the oxygen more or less reactive. Donates electron density into our pi system, so our oxygen becomes what? More or less negative than the aldehyde. Becomes more negative than the aldehyde, which means which one would react preferentially with DIBAL? Our chloride structure. Which means once we form the aldehyde, we've actually stabilized and minimized the ability for DIBAL to react with it. So until we add a second equivalent of DIBAL, the DIBAL is only going to seek out our acyl chloride. We don't have to worry about the aldehyde reacting. And that means that we can stop at the aldehyde formation. If I want to take the aldehyde further, what can I do? I add more. Okay, I could add more DIBAL, or I could switch over to lithium aluminum hydride. Okay, so I notice there's lots of questions here, so let's fire away. Let's see what questions we got. I know you had one earlier.
How come there's no charge? Like when the chlorine leaves, where does the hydrogen come from?
The hydrogen came from our aluminum hydride.
And that's what
That's what's doing our substitution. So let me break that step out again. I have a feeling the two of you in back are asking the same question. We got our carbon, got our oxygen, we form our bond to our aluminum. And I can't for the life of me draw that stupid butyl group. There's our hydride. Our carbon is positively charged at this point. The hydride now slides over to our carbon, and we end up with...
So if we have a chlorine, how come we have two methyl groups on the carbon?
There's our chlorine. There's our hydride. There's our oxygen with the aluminum. The oxygen says I would rather share with the carbon, so it can take the electrons back from the aluminum and kick out the chloride.
So the oxygen still acts as a nucleophile?
I'm not quite sure what you mean. The oxygen acted as a nucleophile all the way through this reaction. And that last step, it's kind of hard to refer to it as a nucleophile because it's part of the structure. So as an atom, does it react with something other than hydrogen? Yeah, it does, but it's reacting with an atom it's already attached to. So it's hard to say it's a nucleophile, because then by that same token, you're saying that carbon in the same structure is an electrophile. But that oxygen is sharing electrons with the carbon. Okay. And pretty much the whole dynamic of that reaction comes about in that very first step. The oxygen has to act as a nucleophile. Aldehydes and ketones have less electron density on the carbonyl oxygen, which means they're less reactive. Which means once we form the aldehyde, it won't react a second time with the DIBAL because it's actually less reactive than our starting material. Okay, in this particular mechanism. Yeah? The oxygen comes from, so at the very end of this, what you'll end up with is an aluminum oxide. It picks up that OH from where? From water that's added as the second step. Just like our, whoops. And then H plus from our water goes to the oxygen on our alcohol.
So it does become an alcohol then?
Oh, in this case, no, it won't. That H plus would be off somewhere else in the solution. Your solution would be acidic.
The solution is acidic.
Yep.
So we just end up with the alcohol, the aldehyde.
You end with the aldehyde. You do not end up with the alcohol. Nope. You said secondary alcohol and aldehyde don't mesh. Those are different classes, right? So we'd end up with a ketone, we'd end up with the secondary alcohol because there is no intermediate stage. A ketone will reduce to an alcohol, period. No other option. The aldehyde is the only one that we're trying to pick up, and that's going to have to come from our acyl chlorides, acids, or esters. Because that puts the carbonyl at the end of the structure. So as we move through, acyl chlorides in a first reduction step become what? Aldehydes. Then they can move to alcohols. Esters in a first step can become aldehydes and then move to alcohols. Carboxylic acids, again, can move from an acid to an aldehyde to become the alcohol. So what's happening is you're stalling that reductive step. Lithium aluminum hydride, because of the mechanism of how it works, won't stop. The aldehyde is more reactive than those previous pieces, which then means the aldehyde reacts before the other pieces get to react, and we end up at the alcohol. DIBAL, because it's a slightly different mechanism, will stall at the aldehydes, And until you add another source of hydride, the aldehyde stays. Because the acyl chlorides, the esters, and the carboxylic acids are more reactive to DIBAL than an aldehyde is. So what's the difference with ketones? When we do a reduction with a ketone, how many reductive steps are there? One. There is only one. So DIBAL is going to give you the exact same result with ketones as it would with aldehydes, or sorry, as it would with sodium borohydride or the other one, lithium aluminum hydride. Okay, so the only real reason that we bring in DIBAL is that we want to do a reduction, but we want to control that reduction, which means we're looking at our acyl chlorides, our esters, and our carboxylic acids. Okay? Which is why we didn't explicitly talk about DIBAL before, because we were really looking at the formation of which functional group? Alcohols. Okay? It is still a reducing agent. It does effectively the same thing as lithium aluminum hydride and sodium borohydride, but we can stall its reaction partway through. Okay? Other questions? Because that then, of course, takes us to another sequence. So, the first one's your straightforward one. And kind of mean you only got one straightforward one. So we've got the acyl chloride. We'll react with our DIBAL to give us just the aldehyde. Okay, so we stall at the aldehyde and we're done with that. All right, so that's our advantage of our DIBAL, just the classic DIBAL reaction. So next one gets a little bit trickier. So we switch to LAH this time instead of DIBAL. But to make it a little bit trickier, we're not reacting with a standard carbonyl. Okay, all of these hydride reagents are polar hydride reagents. We have aluminum acting as a positive and our hydride acting as a negative. So what we would have to do is say, do we have a polar pi bond? Well, the difference between oxygen and nitrogen isn't all that extreme. Guess what? The carbonyl reacts the same way as the imine does, and that's the functional group we've got here. So what ends up happening is we will go through and do a single reductive step. I kind of lost carbons in there. And we end with our primary amine. Okay. Nitrogen is a stronger nucleophile than our water, so we just kind of stall there. And that one simple statement, nitrogen being a stronger nucleophile, is going to become important when we move to the next problem. DIBAL, again, goes through and does a single reduction, which I don't think I gave myself a lot of space for. This is one that you got to be careful with, because it's easy to lose carbons. We've got that structure after our DIBAL. Officially, actually, we can't add the hydrogen yet. Okay, it would be our negatively charged, or we could attach it to the big aluminum structure. We then follow it up with the addition of water and acid. Okay, the addition of water and acid, we'd say, okay, well, just like all our other DIBAL reactions, we would expect to go through and protonate that nitrogen and turn it into an oxygen. What? What happened? If we make that a nitrogen with our hydrogen on it, what conditions are we running under? Acidic and lots of water. Remember how we started today's lecture off with here's the imine, enamine reactions, and we can go in an equilibrium reaction with water and our enamines to take them back and forth between our imines or enamines back to carbonyls. It turns out that when we add water and that acid as a second step to work up this reaction, that acid protonates our nitrogen. That then polarizes that bond so much that an equivalent of water can come in and attack. We'd end up with the equivalent of a hemiacetal, where in a vast solution of water, that reaction continues to run until we kick out our nitrogen, and what we're left with is the carbonyl. Exceedingly tricky, right? Because we're running under, oh, it's just a reduction, we don't have to worry about anything. Water is a very dangerous reagent in certain circumstances, and this is one of them. Okay? Water will go through and kick off our imine and turn us right back around into the carbonyl. Okay? So for those of you that got the imine on there after a single reduction, good job. I appreciate that. That was a fantastic issue, or a fantastic job. You had the right idea. We just now have to realize that you have to look at all of your reagents. You do end up with the aldehyde in this case, not the nitrogen compound. Okay, so it's now tying together all of the chemistry. Yes?
Why did the water?
Water, in the presence of our nitrogen-carbon double bonds, is in a strong equilibrium. As soon as we add in an excess of water, we're going to push that the carbon-nitrogen double bond and turn it right over back to the carbonyl compound.
Will it always be?
It'll always do that. Okay. So you will see this typically show up with another thing that's interesting about it. Our starting material is a nitrile compound. Okay, so that nitrile species is going to show up in the next few slides as well, because we're looking at a carbon-nitrogen triple bond. So that chemistry gets tweaked and messed with as soon as we add this water and H+. I think it was Sarah first, but then come back.
Do we need to know like what picks the hydrogens up, what turns the water into the carbonyl, or do we just need to memorize that it goes?
It's water. It's water that picks it up. It's anything remotely basic. Okay? And a lot of people keep asking this question. I'm telling you, putting hydrogens on and taking them off, it doesn't matter what does it. It's there. It's going to happen. Okay? So you're saying what pulls the hydrogens off of the water once it's attached, if we look at our intermediate? I believe is your question. Is that true?
Yes.
Whoops, I just lost a carbon. Does oxygen want to be positive? No. So what does it do? It takes electrons from wherever it can get them. One of those close sources is a hydrogen. What picks up that H+? It does not matter. Okay? We are in a system that has basic atoms. There's oxygens floating around from more water molecules. Okay? There's a nitrogen floating around with a lone pair. There are tons of species in this solution that could act as a base. Do not get bogged down in what's acting as the base. Look at that structure and say, oh crap, this is acidic. That oxygen wants electrons. It's going to get those electrons from a quick available source. That's from the hydrogen. Okay? Yes, it could pull it from the carbon, but we end up going the reverse reaction. And this is an equilibrium situation. In the equilibrium, we've got tons of water. The tons of water is going to push us towards the carbonyl in our equilibrium, not towards the nitrogen-carbon double bond. Does that make sense? It's frustrating, I know, but that's what you're looking at here. Okay. The most likely species to pull off that hydrogen is going to be water, because it's the one in there in the highest concentration. Okay. And if you absolutely got to show something picking up or giving up hydrogens, redraw the solvent. Okay. Which comes to another issue. When we run this reaction, is it one molecule of each? No, you're looking at probably 10 to the 16th molecules of each. So you're not doing it with just one and one. You've got tons of these things floating around in solution. You have to watch out for those, because that same molecule can act both as an electrophile or a nucleophile or an acid or a base, depending at what stage you're looking at. Right? It's not just as cut and dry as an alkyl halide. It acts as an electrophile. Okay? Unfortunately. So yes and then yes. Oui?
Yeah. Okay. From Okay, we have the nitrogen is positive. Why oxygen doesn't attach to nitrogen?
So this brings up another point, okay? And I keep noticing this mistake too. What does this species act as? This species acts as only one thing. In that black box, what does that species act as? A Bronsted-Lowry acid. It is not an electrophile. I cannot emphasize that enough. To act as an electrophile, what must you do? Electrophiles accept electrons, and they can't be hydrogens. Okay? Everybody's been jumping on that oxygen. I'm glad you're looking for the charges, but you have to take it a step further. Yes, the oxygen is positively charged, but how many electrons are around it? 8. It cannot accept more electrons. That is not an electrophile. So the question that you're asking me is looking at a positively charged nitrogen after it's been acidified. How many electrons are around it? 8. It's not an electrophile. Okay? It helps you to identify where the chemistry is. We see the positive on this oxygen, and yes, we can take a first pass guess and say, yeah, that's an electrophile. Whoops, no, it's not. But it is unstable. How does it fix the stability issue? What does H3O plus do to fix that oxygen being positive? It takes the electrons from the hydrogen, giving us what species? Water and, more importantly, H plus. There's the definition of our Bronsted-Lowry acid. Okay? Don't assume because it's charged it's going to act as something. Look at the charge and evaluate it as the next step. Okay? Carlos.
The nitrogen goes off as NH.
It'll leave as NH3. Yeah.
Does it take the electrons from the bond with it?
You tell me. Should it? So if we do our first step and make that oxygen now neutral, we'd have this species, right? Effectively our hemiacetal, or our hydrate, kind of similar to it at least. What happens now?
The nitrogen leaves.
Is the nitrogen a good leaving group?
Not yet.
No. So what do we have to do? We have to protonate it to make it positive. Now it's a good leaving group, so what does it do? Takes the electrons from the bond, which means our oxygen supplies electrons into our pi system. Okay. So yes, nitrogen has to take the electrons with it. Okay. Why? Because if you follow and look at the leaving group ability at each of those stages, that's why it can leave. Okay? Until you've gotten it to the point where it can act as a good leaving group, you can't do anything with it. The end result, as a final summary again, we end with our aldehyde. Okay? Other questions on that one? So, it's tricky. Watch out for those tricks.
So it's only the carbon-nitrogen double bond that will happen to? Because it didn't happen on the previous thing.
Did we have a pi bond there for the water to react? No. Did we even have an acid catalyst to push that reaction?
No.
No. So it's really looking at, it's the pi bond characteristics, that carbon being positive, that's allowing a lot of these attacks to occur. Until we can force that electrophilic carbon, we're really not getting anywhere with it. Okay. Probably the most tricky one that you could ever see. I doubt that I would ever ask that question, and I don't think it shows up on the ACS. It's just important to realize that that can happen. So, here we go. Synthesis question. I'll give you 3 minutes. That sucked, and you got a good Grignard option. What was that? Nothing. So for now watching the video, you've got this as a possible answer. After that, we're really just looking at our carbon nucleophiles. So what will happen on Wednesday is